We can now wrap up all this work we have studied thus far about EM theory into four neat and succinct equations called Maxwell's equations. Two of Maxwell's equations involve integrals of the electric field E and the magnetic field B over closed surfaces. The first is simply Gauss's law, stating that the surface integral, in other words the perpendicular component of the electric field, over any closed surface equals 1 over epsilon naught times the total charge enclosed within the surface. The second is the analogous relationship for magnetic fields, stating that the surface integral of the magnetic field B, in other words the perpendicular component of the magnetic field B, over any closed surface is always zero. So this is a similar law to this for the magnetic fields. This statement means, among other things, that there is no such thing as magnetic charge or monopoles as a source of magnetic field. The third equation is Ampere's law, including displacement current. So this is the displacement current. And the fourth is Faraday's law. Ampere's law states that both conduction, IC, and displacement current, this term here, where this symbol represents electric flux, act as sources of magnetic field. So both of these act as sources of magnetic field, the normal current and this displacement current. Faraday's law, which states that a changing magnetic field or magnetic flux induces an electric field. So we have here a changing magnetic flux here causes an electric field around a loop. The minus sign there is due to Lenz's law. That's the main equations. Now, comparing equation 3 and equation 4, we see a remarkable symmetry. 3 says that a changing electric field or electric flux creates a magnetic field. Equation 4 says that a changing magnetic field or magnetic flux creates an electric field. Indeed, in empty space where there is no conduction current and IC equals naught, so when this term is equal to 0, the two equations basically have the same form, apart from a numerical constant and a negative sign, with the roles of the electric field E and magnetic field B reversed in the two equations. The same symmetry is also evident in the first two equations. In empty space where there is no charge, the equations are identical in form, one containing electric field E and one containing magnetic field B. But the most remarkable thing about the third and fourth equations is this: a time-varying field of either kind induces a field of the other kind in neighbouring regions of space. As Maxwell recognised, these relationships predict the existence of electromagnetic disturbances consisting of time-varying electric and magnetic fields that travel or propagate from one region of space to another. Even if no matter is present in the intervening space, such disturbances are called electromagnetic waves, and we now know that they provide the physical basis for light, radio waves, infrared, ultraviolet, X-rays and the rest of the electromagnetic spectrum. We can rewrite equations 3 and 4 in a different but equivalent form by introducing the definitions of electric and magnetic flux. So remember, the definition of electric flux is dot product E dot A. Remember, when it's uniform it just turns out to be E, the electric field, times the area. The same with the flux here is B dot dA. And remember, when it's linear it turns out to be B times the area. If we use those two integrals there and just slot them in, then we get this form of 3 and 4, exactly the same. Again, we notice the symmetry between the roles of electric field E and magnetic field B in these expressions. Although it may not be obvious, all the basic relations between fields and their sources are contained in Maxwell's equations. We can derive Coulomb's law from Gauss's law, we can derive the law of Biot and Savart from Ampere's law, and so on. When we add the equation that gives the force on a charged particle in the electric field and magnetic fields, namely this equation here, we have all the fundamental relations of electromagnetism. So with this and these four equations we have everything. The fact that electromagnetism can be wrapped up so neatly and elegantly is a very satisfying discovery. In conciseness and generality, Maxwell's equations are comparable to Newton's laws of motion and to the laws of thermodynamics. Maxwell's synthesis of electromagnetism stands as a towering intellectual achievement, comparable to Newtonian synthesis and the development of relativity, quantum mechanics and the understanding of DNA. All beautiful and all monuments to the achievements of which the human intellect is capable.